and welcome to the Chapter 6, Section 2 notes with inconsistent and dependent systems. This is still going to be solving systems of equations with matrices, but we want to look at the special cases. If you recall from solving systems of equations, you'd have a couple of special cases, which would be, I'm also just going to reiterate the fact that the solution is where the two lines cross each other. In 3D case, we're not dealing with lines, we're dealing with planes, and so it has a little bit different feel to it, but there still is a case where there are no solutions. You know, if you have parallel lines like this, they don't ever cross, and so there's no point that we say is where these two intersect. You also can have the case where a system consists of one line, and then even though there's another equation given, it's the equation for the same line. So there's actually just one line there, and there are infinite solutions because it's every one of these points that's along that line. And those are the two cases that we're going to look at. No solutions, like this, and then no solutions versus infinite solutions. And so let's see about number one right here. We're using Gaussian elimination to solve this system. I'm going to forgo doing the whole elementary row operations thing, and I want to just put this into a matrix over here, make an augmented matrix. This one has 3 rows and 4 columns, and so I'm going to make it be 3 by 4. I'm going to come in here, the augmented matrix, I'm just grabbing those coefficients, so 5, and then there goes 12y, oops, that was 12y, 1z, and then it goes equals 10. So there's the first equation is the first row. Now 2x plus 5y plus 2z equals -1. And then there is 1x, 2y, -3z equals 5. And so these are the equations. I've got my matrix there. I called it matrix B for now. And so I'm going to solve this one by going back into matrices. I want to do math this time, and I'm going to scroll down. It's way down here, looking for reduced row echelon form. And I want to do reduced row echelon form for matrix B that I just created. And I get this one. Okay, so I'm going to write this down, which is that I have 1, 0 with -19, and then this was 0. I'm going to keep referring back. So I have that one. 0, 1, 8, 0, and then 0, 1, 8, 0. And then there was this kind of funny looking row that went all zeros and then 1 like this. Okay, so that's the result. And this is what you would end up with doing Gaussian elimination. It's not even possible in this case to do Gauss-Jordan elimination, which is to obtain the entire reduced row echelon form, because we cannot do anything about these numbers that are in this column right here, the -19 and the 8. And if you think about what these rows represent, they represent equations, and these equations are fine. This equation goes x minus 19z equals 0. That gives a relationship between x and z. There's this relationship, y plus 8z equals 0. That's a relationship between y and z. But then this third equation over here, it goes x, y, and z are all zeros. So just 0 on this side, 0 equals 1. And this is a false equation. It doesn't depend on x, y, and z. It's just false all the time. And so it's impossible to ever satisfy this equation by some x, y, or z values. That means there are no solutions. And one of the big ideas from this section is going to be to state the solution set for these interesting situations. And since there are no solutions, we make the solution set is a set with all the solutions in there. There are none, so we just make an empty set, which sometimes we use special symbol like this, a 0 with a cross through it, and that is the solution set. It's the empty set. So what about this other one? I'm going to put this as an augmented matrix into the calculator. And that for me is going to be matrix C. Got the augmented matrix. I'm going to go back to the matrix, go math, looking for that reduced row echelon form for matrix C. and then we'll see how we need to deal with this one. This is not what we just saw. We just had that row that had almost all zeros, but it has a 1 on the other end. Let's think about what matrix we have now. I will copy this down and refer back to it. It goes 1, 0, 2, 5, and then we've got the -1, 0, oh, I already lost it, 0, 1, -2. And then we got a full 0 row. Okay, so this is the row echelon form, but then this equation over here that just goes 0 equals, because here I'm going to put this dotted line, this is where our equal sign would be on the equations, 0 equals 0, and that equation is always true, as opposed to the last one, 0 equals 1, which is never true. This is always true. It doesn't depend on x, y, and z. We don't need to try to satisfy this. We actually are left to only needing to satisfy these two equations, which these two equations, I want to write them down. The first one goes x plus 2z equals 5. The other one goes y minus z equals 2. Y minus, because it's -1, so -1z right here. And these are the two equations. Now it's two equations, but there are three variables, and so how should we handle this? We still want to come up with a solution set. It's just the case that there are going to be an infinite number of solutions, infinity solutions for this. And so what we will do is going to be called parametrizing the solution set. I'm not going to write set though, because also parametrizing the solution is alright. Now what that means is that we want to describe x and y in terms of just one variable. And in fact, since we're going to use z as the variable that we'll use to describe x and y, we'll also describe z, but z is just z. And so we're going to end up with this thing. We want to have x in terms of z, like it's a function. You know, the same way you can have a function f of x. We're going x of z because we're going to be able to plug in a z value to find out what x should be. That's what we can do inside of this original equation that we have. If we have a z value, we can plug it in, say if z is 0. We can plug in 0 for z, and then we can find what is the corresponding x value, because it only depends on z. And so we'll have x as a function of z, y as a function of z, and then z is a function of z itself, it's just z. And so we want to write our equation like this. We want to write our system, our set of solutions in this manner. And so what is x in terms of z? We just need to come over here, grab our equation x plus 2z equals 5. And then we want to solve this one for x, so we can subtract 2z. And it's going to go x equals 5 minus 2z. So there's x in terms of z. We can do the same thing for y. We started out with y minus z equals 2. So we can add z to both sides. Y equals z plus 2. And so that's y in terms of z, and now we're ready to write our solution set. It's all of the points that go, the x value is 5 minus 2z, for whatever z is. Y is 2 more than z, z plus 2. Z value is just there. And then I'm going to go with colons right here, which you pronounce out loud, such that z can just be any real number. And so what we have is that the solution set is the set of all these ordered pairs that go 5 minus 2z, z plus 2, and z, such that z is a real number. And then if we wanted to just start listing some of the elements in here, then we just need to find z values to plug in. What if z is 0? Plug in 0 for z, it's going to go 5 minus 0 is 5. If we go 0 plus 2, we'll get 2 for y, and then z we already said should be 0. And so this would be one of the solutions. I'm going to go dot, 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 because those solutions, there's infinite number of them for different values of z. And we don't have to just plug in whole numbers for z. We can plug in any numbers and get corresponding x and y values, and then we will have ordered pairs. So we know that out of these infinite number of solutions, one of them is 5, 2, 0. And so what about a system like this? This one just already starts out as being two equations with three variables. To get one solution, if we have any hope of getting one solution, we need the number of variables to be equal to the number of equations. I will say to get one solution. So there's no hope that we will get one solution. That's for sure is going to be a special case. Whether there are no solutions or whether there are infinite solutions, that's still up to us to find out. This matrix, it's still fine to plug it into the calculator. And so I'm going to do that. And I have this augmented matrix. This time it's matrix D, so I'm going to go through this rigmarole. I do need to quit out of there. I don't want to keep modifying that matrix with anything. So I quit out, go back to matrix, scroll all the way down, reduced row echelon form for matrix D this time. And these ones, I think that if I would have gone math, convert to fractions, there we go. Unless you could just recognize that those are -1/3, but with fractions, I like that a little bit better. So we get this reduced row echelon form, 1, 0 with the -1/3 and 1, and then we had 0, 1 with the -1/3 and 1. I think that was the right one. Oh, that's 0 over on this side. And so we have that thing equals 0. And then we're going to carry on just like we did before, parametrizing the solution, because we have our first. And that's why we get reduced row echelon first. It's because we don't want to have 3 equations in the same variable. If we can get it down to 2, then we can parametrize. And so this first equation goes x minus 1/3 z equals 1. So we can solve for x in terms of z. I'm just going to add that 1/3 z over. So it's going to go equals 1 plus 1/3 of z. The y equation is pretty similar. It goes y minus 1/3 z, this time equals 0. Still want to add the 1/3 z over, get y equals 1/3 z, and then we are right up to the end because we're going to go, the solution set is all of these ordered pairs where the x coordinate depends on z like this, 1 plus 1/3 of z. The y coordinate depends on z just by going 1/3 z, and then z is itself. I'm going to go such that here z is allowed to be any real number. If we had some kind of real life scenario or real life application, that might place some reasonable limits on z. You know, if we're making a graph about selling units or something, maybe x, y, and z are numbers of units of different things like shirts and pants and hats or something, then you can only sell positive numbers of units, and also you sell whole numbers of units. So z cannot just be any real number, it should be positive integers in that case. But here, this is a real theoretical case. We're just dealing with some planes, and so they intersect along this line over here. And that is what's going on. If I can manage to draw this in space, there is some stuff in the notes about this, but the idea is that when you have 2 planes, here I'll try to draw a plane. So this plane, it's kind of at an angle. See, this is the x-axis coming out, y-axis, z-axis. So if you have a plane, it's kind of at an angle over here, and then we have some other plane, which comes like this. It's passing behind there. I will draw some dotted line here. And so these planes, see, they're intersecting on these 2 points, and then they intersect along a line like this. And so planes actually intersect, 2 planes, they intersect along a line. That's if they're not parallel. If 2 planes are parallel, then they don't intersect at all. And then we could still have the case where we're just dealing with the same 2 planes, and then there would be an infinite number of solutions. But instead of being all the points on a line, it would be all the points on the whole plane. Here, though, we ended up with one of these kinds of cases. We had 2 planes. They're not parallel or anything. They're not the same plane. So they intersect along a line. And the equation for that line, those x, y, and z coordinates that fall along this line over here, they have this characteristic to them. And that's how we're parametrizing it. And so we will carry on and go for an application problem right here. And the reason why I am solving these matrix problems on the calculator so much, I really recommend it just because what ends up being the hard part, and what should be the hard part of these kinds of questions, is actually coming up with the equations that you need. It's not to do the number crunching, because that's all fairly tedious. It's just normal arithmetic. You know, it's elementary school arithmetic, doing plus and times by whole numbers and all of this. So I'm not too worried about the matrix. You should know how to do elementary row operations, just individual ones, but it can become a bit of a nightmare, always just trying to do all of the whole Gaussian elimination by hand. So here I want to focus on what we can do to try to come up with an equation to describe this scenario. We're looking at 4 one-way streets. The arrows are not very clear, but this one is traveling south. This road over here is going to the east. I'm just calling this north, south, east, west over here like this. And so this street's going north. And then this street, oh, it's also going east apparently. Those are going the same way. And so what do we have? We've got these 4 intersections. Intersection 1, intersection 2. We've got intersection, oh, they're going by clockwise, 3. And then the last one, intersection 4. And we're looking at traffic here, and something we could say about traffic patterns is that in each one of these intersections, the amount of cars that are coming in, which would be these cars, the ones that are coming in there, that should be the same number of cars that are leaving. And so these cars over here are headed out of the intersection. These ones to the east, these ones to the south. The number of cars coming in must equal the number of cars coming out. And that is set up explicitly for us right here. It tells us that should happen. Of course, it makes sense. Otherwise, there's just cars piling up in the intersection, or else some cars are being spontaneously generated or something. That doesn't make sense. And so cars in equals cars out. I'll even just write that. Cars in, that equals cars out. And I'm going to do this for intersection 1, 2, 3, and 4. And so we'll come up with how many cars are coming in to intersection 1. There's 180 cars per hour coming in from the west, 200 cars per hour from the north. So that's 200 plus 180. Those are coming in. Now which ones are coming out? It gives us variables for those. W are headed to the east, Z are headed to the south. So the number of cars out are W plus Z. And then for intersection 2 over here, this time the cars coming in are the variables, W and X. This X over here, because those are headed up, those are entering the intersection from down here. W and X are coming in. And then the ones that are coming out are these ones, the 400 and the 200. So I'm just going to, for now, not simplify anything, just write everything down. Intersection 3, there are, oh, this time we've got combination of numbers and variables, because this Y that's coming in over there, Y is coming in. Also 200 cars per hour are coming in from the south, so Y plus 200 equals the cars that are leaving. X is coming out, and then 30 is also coming out. And last but not least, we got intersection 4. The Z cars are traveling from the north. They're entering the intersection, so Z is coming in. Also these 70 from the west, those are entering, so Z plus 70 equals, I'll make that 7 a little better, equals how many are coming out of this intersection? It is Y is coming out. Oh, and also 20 down here. These are exiting to the south, so Y plus 20. Now we're getting along our way. We've got 4 equations, but these ones are not in the standard form that we should have for making the augmented matrix. We need to have our variables all in the same order. Our augmented matrix that we should come up with, it should be W, X, Y, Z equals something over here, just numbers. I'll put number right here. Coefficient for W, X, Y, and Z in that order, and then equals some number. So we need to rearrange these equations to get them in this order. And so what I want to do, well, this is just going to go 380. W plus Z equals 380. I'm going to write it like that. W plus, I'm going to skip some space just because X and Y should be here. W plus Z equals 380. Then we've got W plus X equals 400 plus 200 is 600. Now we have Y plus 200, but what if we subtract the X over onto this side? Also subtract this 200. Oh no, then we're going to have negative signs here. Scrap that. That's what, it looked okay at first because it feels so natural to put everything on the left side. But I want to reverse that. I want to subtract the 30. Minus 30 over here and subtract the Y. And so we end up actually, these y's cancel, these 30s cancel. We have this equation on the right side, which I'm going to make that be the left side now. X minus y equals 200 minus 30 is 170. I was nervous about those negative signs. And then what about here? I want to do the same thing. Move the numbers to the left, 70 minus 20, and then subtracting z. This 20 goes away, the z goes away. So now it's going to go y minus z equals 70 minus 20 is 50. And this is the right order for everything. We've got w, and I'm going just the first equation now. I'm going to make augmented w. There are no x's, no y's. 1z equals 380. Then we've got w and x with no y or z. That equals 600. We have no w's, and then x and minus y, no z's, equals 170. Then we've got no w's, no x's, y minus z equals 50. And so this becomes our augmented matrix. Now let me put that in the calculator to solve it. Even though there's so many ones and zeros, this one would be pretty nice to solve by hand. Not too many steps or too much crazy fractions or anything. But nevertheless, bring up the handy dandy calculator. And here I have my augmented matrix. It's matrix E this time. I'm going to quit out of there, go through, find math, reduced row echelon form. Getting used to this. Matrix. I want matrix E this time. And then here we go. Reduced row echelon form. We've got ones over there, one with the minus ones. And I believe I've transcribed it over here. Looks good. Getting rid of the calculator. So we end up with this system. And I already did the Gaussian elimination, so we end up with, over here, some equations. That's what I'm interested in, is which equations are represented by these rows. We have an equation that goes x plus, oh wait, that wasn't x, that was w all the time. The first coordinate was w this time. I'm used to the 3D case, so we had w, x, y, z. So there's w plus z equals 380. Then we've got an x minus z equals 220. And then y minus z equals 50. That last row is just going 0 equals 0. So now we're in the infinite number of solutions case. And we've got here always pairs of variables inside of these equations, and the natural choice for a parameter is z, because here it's no problem, we can solve for w, x, and y all in terms of z. So I'm going to do that now. Here we're going to subtract z, so we get w equals 380 minus z. X, I will go with the x next. There we can just add z, so plus z on this one, plus z. So we're going to get x equals 220 plus z. And then we got to add z for the y's as well. So we'll get y equals 50 plus z. And now our solution set, we're ready to go. It goes, the w coordinate is 380 minus z. The y coordinate, I keep saying y after, but it's x 220 plus z, y 50 plus z, and then the z coordinate is just z. And I'll say such that z, I don't even want to say real number this time, because you can't have a real number of cars. You could only have a positive whole number of cars, and so I'm actually just going to go, z should be a natural number. Those are the numbers going 1, 2, 3, 4, 5, like that. Even though z, it could be 0, but let's just roll with it. This one I'll say z can be 0, or these positive whole numbers. And so now, what about this part? If construction limits z to 50 cars, how many cars per hour must pass between the other intersections to keep traffic flowing? So it's just asking us what is going to be the solution when z is 50. So we just want to plug in z equals 50. We know that there's going to be w, x, y, z is 50. And then we should go for the y coordinate, 50 plus 50, that's 100. 220 plus 50, that's 270. And then 380 minus 50, that's 330. So that is, it only asks about the other intersections. So W, X, and Y, that's really the ones it's looking for, but we should get these values. All right, so that does it for this section. I hope that this video was helpful to you, and I will catch you in the next one. Thanks.